force is stronger than we. Microsoft makes me delay my lecture for 2 minutes, which is good because, well, first things first. Things must work the way they must. That's it. It's a very simple rule. All right. Okay. Hater's gonna hate, catcher's gonna catch. Physics works. If you put some will in it, no, it's more will power. Bless you. And ability to make things work. So I'm gonna finish this current topic probably in 10-15 minutes tops. Then we're gonna have Q&A session. If you have any Qs, I may give you A's. After that, I'm gonna start new topic, which is supposed to be, well, already started. Come on. So I'm a little bit like 15 minutes behind the syllabus, which is fine. Usually it's more than that. I don't want to use that computer unless I have to. And before I forget, yesterday I forget. Okay. Mostly I just want to test. Is it, again, only red day? Or today we're allowed to use other colors too? Green. Green is green. All right. So, please keep that in mind. Although I don't expect many students doing homework from 6 to 10 a.m. on Saturday, but just in case. An equation at the top tells us how to calculate work when a torque makes an object spin about a fixed axis. But basically, we don't really need that equation. We need this equation. This is old-fashioned work kinetic energy theorem. And we just have to say something new about kinetic energy. When we have an object which makes a translational motion with no spinning, kinetic energy is equal to mass speed squared over 2. And when an object is large, we didn't ask speed of what? Well, the answer is doesn't matter. Since it's translational motion, every single point has exactly the same speed. So we just usually use a speed of center of mass. But when object spins, speed is different everywhere. Closer to the rim, points travel faster, then slower and slower. So we need a way to calculate rotational kinetic energy. And it's very simple. Since we know how to calculate kinetic energy for a single point, we just use this equation, and we use the fact that they all have same angular speed. We just need to make a transition from linear variables v to angular omega and add all individual kinetic energies. And since speed is the same, it's a common factor. What we have for kinetic energy of spinning object is a very simple equation, 1/2 times moment of inertia times angular speed squared, very similar to this, to translational. But instead of mass, we use moment of inertia. Instead of speed, we use angular speed. And now, when we need to make something spin faster or slower, we change rotational kinetic energy. And to do that, we need to do some work. And the work kinetic energy theorem says change in the kinetic energy is equal to the net work acting on this object. Nothing new, basically. So we can start solving problems. So we want to spin an object from rest to a given angular speed. This problem is just about units, basically, because the equation is very simple. What amount of work has to be done? Well, the amount of work, total amount of work by everything else acting on this should be equal to kinetic final minus kinetic initial. This equation is not new. The new part is how do we calculate kinetic energy for a spinning object? Well, initial was 0 because it was at rest. And the final should be equal to 1/2. Now, instead of mass, we should use moment of inertia. And instead of speed, we should use angular speed. Well, final, of course. And now we can make mistake only if we don't convert units correctly. What should and what should not be converted? Well, kilograms. Well, first of all, what is it? What shape? Disk. So I've seen many times people wrote 1/2 and then mr squared. Well, omega final squared. What is wrong with this expression? The moment of inertia of a disk is indeed 1/2 mr squared. Nothing wrong about this. This is correct. This is wrong. Please tell me what's wrong with that. That's correct. That's wrong. That's correct. Yes. Exactly. Exactly. And that happens a lot. This is a different half because of the equation for kinetic energy. And this half should be because of that equation. So it's 1/2 times 1/2 mass radius squared. So it's going to be 1/4 times mass. Kilograms, correct unit. Centimeters, keep or convert? Convert. 0.1 of a meter squared. Revolutions per second, keep or convert? Convert into what? Radians per second. So it has to be squared. 100 revolutions per second. So seconds already a good unit. Revolutions. How do we get from revolutions to radians? 1 revolution is equal to 2 pi radians. Now I just need to take a calculator and calculate this number. What do you expect to have for a unit? What should be the unit of that final number? So So, anyone, please tell me the number. Yeah, the final number. 0.8. So we can just round it up to 50,000. What? Oh, 5,000. Yeah. 5,000 what? What unit should I write? What did you say? Joules? That's work. Doesn't matter. Rotational kinetic energy, translational kinetic energy, work kinetic energy, any kind of energy, still joules. So, interesting. Okay. Colors work. Now eraser doesn't. All right. Microsoft screwed me. They broke the new drivers now conflict with the software. So I'm going to keep that there, but I have to start here. Because what is written on that screen is not a part of a presentation. It's a different layer now. But we want to keep it inside the presentation, so I always have a backup. Well, now we can move on to the final topic of this conversation, rolling. And we know what it is. It's a combination of translational motion, like this, a translational motion, rotational motion. When it's happening together, that's what the rolling is, translational and rotational. However, there are several types of rolling. Sometimes, if you go to a bowling alley, you throw a ball, it doesn't roll immediately. It slides first, and then something is happening, and then it starts rolling. So in that situation, there is a motion of a spinning object relative to the surface. We don't call it rolling in our sense. In our sense, rolling is happening when there is no relative motion, no slipping. In that case, translational motion is being coupled very easily with rotational motion. No slipping, no slipping, no slipping. Well, this is a ruler about 2 meters long. So if we take a look at this red label, and I roll this wheel until it makes one complete revolution. Here. One complete revolution. So what is the distance traveled by this red dot? One complete revolution means a circumference. So this length, now should be equal to practically 2 meters. If I could bend it, this meter, I could make one revolution about this. But on the other hand, that's exactly the distance traveled by the center of mass. So we can make a very important conclusion. For the rolling with no slipping, when translational motion is coupled with rotational, distance traveled by the center of mass relative to the ground is equal to the distance traveled by any point on the rim relative to the center of mass. And distance divided by time is speed, etc., etc. So we can correlate, relate, couple linear variables which describe the motion of the center of mass, speed of the center of mass, acceleration of the center of mass, distance traveled by the center of mass, with rotational variables which describe rotational motion about the center of mass, like angular speed of that red dot. And this is the equation, the same equation we've used before. And this is very important, so if you have any questions, please ask. This is a speed of that dot about center of mass. If you imagine an observer sitting here at the center of mass and looking at that dot, red dot, of course, for that person, the whole world would be spinning, but who cares about that? For that person, that red dot moves just in a circle, and speed equals distance over time or circumference over one period. But the center of mass travels relative to the ground the same distance. So for the center of mass, speed will be equal to distance traveled over time, and they equal. Equal distance, equal time, equal speed. So now everything becomes very simple because technically we don't need to learn anything new. Rolling is just a combination of what we've learned before. We know everything about translational motion. We know everything about rotational motion. Now we just need to combine those two together. That's it. For example, kinetic energy of a rolling object should have now two parts. One half mass speed squared. This term describes translational motion, how fast the center of mass is traveling in space. 1/2 I omega squared. This term describes how fast parts of this object spin about center of mass. So now for a rolling object, total kinetic energy is just the sum of two terms. But with the rolling with no slipping, these terms are related, not independent, because these speeds, linear speed of the center of mass and angular speed about center of mass, are coupled, are related. So we can always use this relationship to simplify this equation any way we like to. In general, when something rolls, in addition to kinetic energy, potential energy might change. Gravitational potential energy changes only when an object changes height. If it goes up, potential energy increases. If it goes down, potential energy decreases. And, well, this term, work of applied force, describes if something else is touching, like a hand, like this, or it's attached to a motor, electric motor, and that makes it spin. So in general, we should use that term, but if something is just getting pushed and rolls on itself, there's only kinetic energy, and potentially there is potential energy. That's it. And now we are ready to solve a couple of more problems. A ball. Why is it important to name the object? What is the difference between a ball or, let's say, something else? Yes? it tells us the shape, a ball is a sphere. So if we want to use equations correctly, we have to use a correct expression for the moment of inertia. That's it, nothing else. So what's happening here? It rolls already. We don't know how it was brought into the motion. That doesn't care. We shouldn't care about that. It's not important. It's in the past. So, of course, something was acting on it some time ago. But after that, it's just rolling like this with constant velocity. And if we want to stop it or something, we have to apply a force to it. For example, like this. So here, the friction between my hand and this ball applies a force which stops it from moving. Of course, when energy changes, the work is done, and the question is now, how much work should be done? Well, we know what to do. We've done it before. So initially, it was traveling at 2 meters per second. This is what? This is the velocity of the center of mass, technically, center of mass. But also it spins about the center of mass. And eventually it stops. Let's see. So, network, that amount of work we need to calculate, supposed to be equal to the change in the kinetic energy. Well, normally, the word how much means we need to calculate the magnitude of it. Yeah. So, final minus initial. Now we need to say that when it rolls, the kinetic energy should have two terms, translational and rotational. Oh, okay. Now we have to apply write two equations. V squared over 2 plus 1 I omega squared over 2. Now, well, for the first equation, we now know everything we need. 5 times 2 squared plus 1/2. Here, we have to apply an expression for the moment of inertia of a rolling sphere. And here, we need to write an expression which relates angular and linear variables. This equation, which we can always apply when an object rolls with no slipping. And some people would say, after reading this problem, we don't know the radius, so we cannot solve it. But as you know, we have to believe that it's solvable and just push ourselves ahead. And if you look closely at this expression, what do you see? It's getting cancelled. So I give up. So what we have here is 1/2, so that's going to be 10 plus, I want to cross out r's, and what's left, it's going to be 1/5 times, and speed is 2 squared, 4. Wherever it is, so for 1.11.25 joules. No, it's 4. It's not 5/4. It's 4/5. Right? $10.8. For some reason I switched. 10.8 joules. It's not 5/4. It's 4/5. Yes. Cannot hear you. Oh, I forgot the mass. So if I forgot the mass, okay. If I forgot the mass, I should add it here times 5, right? 5, so 5 and so 2 and 2, 5 and 5 only, so it's going to be 14. Yeah, thank you, because I remember it was a simple number without decimals. Well, now a solid cylinder rolls down a ramp. You're going to see how it's happening soon. First, let's solve it. (30°). So it traveled 4 meters. Where should I write this number? If we write this number at the correct place, that's it. The rest is actually very simple. So the only mistake people usually make is, where is 4 meters? What do you think? The hypotenuse is traveling. Traveling means actual distance traveled. Yeah? So this is 4 meters here. Now, do we have anything like strings, hands attached to this cylinder? No. So we can just write that kinetic initial plus potential initial should be equal to kinetic final plus potential final. Again, we write this equation because nothing like this is happening. No slipping also means there is no kinetic friction between this object and the surface, which is good. So 0 plus mg height initial should be equal to, well, now we need to remember that it will also spin. That's what sometimes people forget. It will travel, but also will spin. Final. If you don't forget that, And if you write both terms for rotational and translational kinetic energy, that's it, you're all set. Now, 2 times 10 times, what number should I write for the initial height? 2. This part comes from a right triangle. Should be equal to 1/2 times 2 times, that's what we are looking for, plus, I want to continue here, plus 1/2 times. What should I write for the moment of inertia? That's a cylinder or a disk, a solid cylinder or a solid disk. 1/2 times mass bless you. 1/2 times mass times radius squared. One half times two times radius. Do you see any number for a radius? So what do we do? Well, we always have two choices. Always have two choices. The first choice is what? To give up. And the second is not. That's it. So what do you suggest? What should I write right now? R, that's it. Absolutely correct. Nothing else. Squared. If we know a number, we write a number. If we don't know a number, I don't know how many times we've said that, we write a variable which represents the number. If we know a variable, we use that variable. If we don't know a variable, we use it like we know it. That's it. Times. Now, it should be angular speed squared. And the angular speed for the motion with no slipping is related to the linear speed. So we should write final speed over r squared. And so lucky we are again. It's a good day to be alive. Radius getting cancelled. So, well, hence, we have an equation. On one side of the equation, we have 2 times 10 times 2, 40. On another side of the equation, we have v final squared plus 1/2 v final squared. And I believe you can solve this equation without my help. I want to believe. And I know you know how to solve it, right? All right, now we just have to do it backwards. We give it a push with the initial velocity, but it spins, but eventually it stops. It's the same ramp, 30 degrees, and it should travel 40 meters up. So it will be h, which is 2 meters higher. So kinetic initial plus potential initial, kinetic final plus potential final. What do we have? 1/2 mv initial squared plus 1/2 I omega initial squared plus 0 should be equal to 0 plus mgh. What else do we know? We'll also know that this should be equal to 1/2 m r squared, and we also know this is coupled And if you look at this equation and compare with this equation, it turns out this equation is exactly the same mathematically. It is exactly the same equation, which was the difference between sliding up and down the ramp with friction. But here, friction doesn't mess equation up, so in this situation, actually, there is no difference at all. Mathematics is the same. Answer will be the same. Any questions? I think this is one of the clearest topics. Just don't forget units, coupling equation, omega equals V over R. And that when something spins, it also has rotational. Yes?
How would you do it if it was sliding?
That's for a Q&A part. That is for a Q&A part when we stop talking about this and open session to the questions. Please ask again. Yes? In this situation, this is the initial speed, and final speed will be 0. Oops. Here, this was the final speed when it starts from rest, and numbers will be the same. That's it. Different type of speed, same number. Well, it's going to take you some time to read all the possible answers. So I'm going to use this time you need or want to teach physics, you got to be strong, you got to be brave. So that is the same question, so keep answering. And also right now, based on your answer to this question, please answer the next question at this immediately. These are 3 shapes we're going to talk about. Sphere, a solid cylinder, hollow cylinder, or a ring, if you look at it like this. They have the same mass, about half of a kilogram each, and they have the same size. The sphere is slightly bigger, but doesn't really matter. And we're going to roll them down this ramp. Same mass, same size. The only difference is the shape. The shape affects the moment of inertia, and one of these answers is correct. We can rank these based on moment of inertia. And in the end, if we start them rolling from the same height at the same time, like this, today you choose the wrong location. You can move back for this demonstration, actually. So I'm going to let them go. They're going to roll down. These are only options we have. The question about which object will reach the finish line the first, travels this distance fastest. It's going to be either a sphere or a ring. A ring means hollow cylinder, or a disk or a solid cylinder. Or they might reach the finish line at the same time. Three-way tie. So you still have about a minute to enter your answers. Okay. What's your choice?
Ring.
Why? So if you answer question number 2 first, what ranking do you choose?
Ring, disk, sphere.
Ring, disk, sphere, number 5. So the most inertial object is this. The most inertial, right? It has most inertia. What does inertia mean? Resistance to the motion, yeah. So this has no friction, very little of inertia. This is how fast this thing travels. This sphere, do you think it has more inertia or less inertia than this cart?
More.
Why? Because it also rolls. So there is translational inertia and rotational inertia. Can I zoom it? No, only a small part. Okay, we'll see. Anyway, better than nothing. So, less inertia, more inertia. More inertia loses, less inertia wins, right? So based on this thinking, this should what? Win or lose? Lose. And this should win. That's it. More inertia loses, less inertia wins. That's physics. Thanks. But of course, would be nice to actually solve it mathematically, and let's do it very quickly. It's just, again, a straightforward application of the law of conservation of mechanical energy applied to the rolling. So in this situation, sphere wins because it has the least amount of inertia, so it's easier to speed it up than other objects. This is how we rank. We'll just look at the coefficients. There's an invisible one here. If you didn't see that one, that might why you rank differently. But if you see it, these are numbers. So answers, and of course, we wouldn't have to solve this problem 3 times. We would do it once for all, because the moment of inertia for all of them has exactly the same structure: form factor, mass, the radius squared. And this is just, again, same old, rolling down a ramp. So initial height starts from rest. Kinetic energy final should be equal to mgh. So what do we write? 1/2 mv squared, well, final, plus 1/2 I omega squared final equals mgh. And let's keep it consistent, capital H, capital H, capital H. So 1/2 mv final squared plus 1/2 times the moment of inertia, angular speed, coupled because it's with no slipping, m goes away, r goes away. What's left? 1/2 v final squared plus 1/2 form factor final squared equals gh. Of course, now we can solve it for the final speed. And final speed goes down when the form factor goes up. If we solve it for final speed, it will be the slide with the exact solution. We will see, C, form factor, goes in the denominator. Yeah. Final speed squared will be equal to 2gh divided by 1 plus that form factor. We increase form factor, we decrease final speed, and well, that is the distance traveled, L. The fastest way to relate distance, speed, and time would be using the actual average speed, because V average on one hand equals distance over time, but on another hand, for the motion with constant acceleration, and this is the motion with constant linear acceleration for the center of mass, it also equals initial plus final over 2. So we can solve it for time. L over V final. So if speed goes down, time goes up. If this goes up, this goes down. If this goes down, this goes up. More time. It takes more time. More inertia, more time. I think it's very neat type of work. Well, I got all calculations here, same reasoning, and again the answer, and that's what we have learned for 2 weeks and more. I think it's impressive. You should congratulate yourself. Now, I have noticed in 4 weeks, people practically haven't been using Piazza for online communication. I don't know why. So yesterday, just for fun, as an experiment, I've created a Facebook page, PY105-106. I'm already friend with that page. I think, I don't know, I'm not sure how the settings work, but I think you don't have to be friend to post anything. And you don't have to use your own account if you don't want to, because all I did, I just created an email. Anybody can do it for free, and then I used that email to create this page. So you can do it. So you can try. If you don't like Piazza, you can try Facebook. If you don't like Facebook, tell me what you like. Twitter, Snapchat. Now, please start asking questions. As long as you stop asking questions, I'm going to start the new topic. Just sliding, up or down? Up. So we have a block or a box. It doesn't roll. Sliding means it doesn't roll. So we give it a push, and it starts sliding up with the initial velocity. This is height, some angle, and that's a distance traveled. Let's say it doesn't really matter, but let's say it stops right at the top, so the final speed will be 0. Well, first of all, we can solve it using Newton's second law, because we've done it before. Net force equals mass times acceleration. Now we can also apply law of conservation of mechanical energy, but if there is friction, just for the sake of solving the most general problem, it's, from my point of view, more convenient to use work kinetic energy theorem. Again, it's the same law, but here kinetic energy final minus kinetic energy initial should be equal to the net work done by all the forces. Kinetic final is 0. Kinetic initial is basically what we're looking for, 1/2 mv squared. So the most interesting part is writing an expression for the net work during this process. Well, what is work related to? Whether we like it or not, it's related to 3 variables in general. For the constant force, work is equal to magnitude of the force times magnitude of the displacement times cosine of the angle. So why is it important to say it loud? Because it forces us to think about forces. So we still have to draw something in a form of a diagram. There is force of gravity, there is normal force, and force of friction in general. So in general, we should write 3 terms for the net work: the work done by the normal force, the work done by the force of gravity, the work done by the force of friction. Well, work done by the normal force is equal to what number? Okay, see here, what do you think? 0. Because the angle between normal force and displacement is 0. The work done by force of gravity. We can use a definition, I calculate that work, but we also can use a given expression which has been derived for the work done by gravity. mg times initial height minus final height. So in this situation, that's going to be equal to mg times, well, of course we set the origin to 0 level at the lowest, so that makes this 0, let's see, minus, well, height is h. Sometimes we know the height, sometimes we need to relate the height with, let's say, distance traveled. In that case, we can use geometry. And friction. Well, for the friction, we know that the angle always equal to 180. So it gives a minus. And friction equals coefficient times normal force. And that's supposed to be distance traveled. So what should we write for the friction? A minus, a coefficient. I'm going to move the distance over here. And the last, the trickiest part is writing an expression for the normal force. But it's not related to this situation. That's related to situation studied 3 weeks ago. And for the normal force, the expression is mg cosine theta. This is this theta. The rest depends on what we know, what we're looking for, but that is complete general solution. You can see actually, well, that we have a minus here, and a minus here, which is a good thing. We can multiply the whole expression by -1. It makes everything positive, and solve it for this square root of that. That's it. Next question, please. Yes?
One more question was about finding like the initial height of a roller coaster car in order for it to make its way all the way around to. Is that on the test? How to do it?
Everything which on the homework in a class or in a lab might be on a test or similar to that. So this is everything. This is similar. Do you have a specific question about that problem?
Can you just explain that?
Of course. First of all, this is only a part of a roller coaster. An actual roller coaster has many more loops and many more parts. So what you see should excite your imagination, and in your imagination you should see the whole roller coaster. And the whole roller coaster has, well, something like this, maybe, or like this. We don't know. It's an alien roller coaster. The thing is that there has to be a point which is above this loop. It actually doesn't really matter technically if we neglect friction. It doesn't really matter if it's here or there. Let's say it's here. So this is the picture which was given to us, but we, in our mind and in our notebook, we have to extend this picture to an actual kind of roller coaster parts. So here where you start from initial velocity equal to 0. And then you start sliding, sliding, sliding down, then up again. The trajectory, the actual trajectory doesn't matter. If we neglect any friction, the length of the trajectory doesn't matter. What matters is that eventually you get here, and when you're here, you're traveling at speed which was found in part A. And what people try sometimes to do is to calculate the height from the ground. But that's not what we are looking for. What we asked for is how much higher. This is what we are looking for. It's all in words. How much higher? Well, in our approach, we can set this to 0. This is final, actually. And this initial, what we are looking for. And all we need to do now is just write the straightforward law of conservation of mechanical energy. Since no friction, The fastest way to solve this problem is to apply a law of conservation of mechanical energy. Kinetic initial plus potential initial equals kinetic final plus potential final. Kinetic initial is 0. Potential initial has that unknown, which we are looking for. Kinetic final is 1/2 mv squared from part A, and final height is 0. You got to cancel the mass again. Very often, well, probably 9 problems out of 10 related to gravity don't rely on mass. The mass usually is getting canceled, which is a good thing. So if we remember that, and if mass is not given, again, just power through, it should be canceled. If everything is worded correctly, it should be canceled. Which are what? What? VA, this is a homework problem. The question was about second part of that problem. In the first part of that problem, you already found this speed. It's a known number. Next question, please. Yes? So it's getting stuck in the bullet, because there is another problem when it's getting through the bullet. Well, so first, this problem, I can give you what to look at. There are a couple of slides related to a so-called ballistic pendulum. And this problem physically is identical to that problem because both problems have 2 parts. It's a 2-step problem. And these parts have names. First part is called the collision. In homework problem, second part is called sliding. Here it's called rising. It's very important to know the names because each name represents a set of laws and equations. And for the collision, we always write a law of conservation of linear momentum, and sometimes maybe, but not in this situation, a law of conservation of mechanical energy. For the sliding, we have a choice. We can use Newton's second law plus equations for the motion with constant acceleration, or we can use law of conservation of mechanical energy, also known as work kinetic energy theorem, if friction is involved. And this is a part of the reasoning which we have to apply in any situation like that. A 2-step problem, we call a name for each step. We realize what phenomenon is happening, and we realize what set of equations we must use, and then we start using those equations. So for the collision, M, big M, V, and here we should call V block. I don't want to call them initial final. That's actually confusing people sometimes. So mv plus 0, because the block was at rest, should be equal to m plus m times v block, well, with the bullet. BB, block and bullet. Second part, sliding. Well, here we have some friction. And it stops. Here I can say final is 0. So the block with the bullet slide. So they must have kinetic energy. Can I call it initial here? No potential, everything is horizontal. Now we need to add, sorry. I don't want to use law of conservation of mechanical energy. I want to use work kinetic energy theorem. So final kinetic energy minus initial kinetic energy, that should be equal to net work. And net work is equal to normal force, gravity, work done by friction. For the work done by friction, we have an equation written just 5 minutes ago. -1 because of cosine, coefficient, normal force, distance traveled. Normal force in this situation is just mg. Everything is horizontal. And, sorry. When I said m, I meant total mass. So in this situation, that is total mass. Now, the only statement which is left to be made is, when we have two parts of a motion or anything else, last things, final things for the first part becomes initial things for the next part. In this situation, the velocity which is final for the first part, that becomes the initial velocity for the second part. That's a very important statement. This, whereas physics is actually getting interesting here. So what are you looking for doesn't matter. I've never asked the question, what are you looking for? Because it is never right question. The question is, how can we relate variables? And this is how. Now you can start plugging in all given numbers to you. And you will see that last equation will give you the number for this. And if you know the number for this, which is turned out the same as this, you can use it here to get the number for that. Yes? When we solved a problem about rising here, the first part was exactly the same as here, but since it's not sliding, since it's rising, no friction, and tension doesn't do work, the equation was m plus m v squared over 2 was equal to m plus m gh. Initial kinetic energy of the system completely transferred into potential energy of the system. Second part in both situations is related to things happening to energy. What kind of things? That depends. Here it's related to potential energy. Here it's related to work done by friction. Next question, please. Next question. Next question. Yes? So if you have a ball on a string making circular motion in a horizontal plane, like this?
Yes.
Okay. So first of all, this is not this. Agree? Here, let's say we pull on a string or something else is happening. Everything is vertical. Here is not. Mg is vertical, but force of tension now is not vertical. That makes a big difference. Because now, well, actually, if we write the Newton's law looks the same. The Newton's law never depends on what is happening. But the application of Newton's law will be completely different, because here everything is vertical. In my example, T minus mg equals ma. So we're just pulling up on a string. But here, we have to use vectors T plus mg equals ma. Well, we can use vectors here, technically T plus mg equals ma. Now, well, let's say something about angles. That's usually the angle. So that's the angle. Now we say that's a right triangle. We know what to do about it. I want to do it as accurate as possible. Okay. In this right triangle, the hypotenuse is equal to the magnitude of tension. The vertical side is equal to the magnitude of force of gravity, and the horizontal side is equal to the magnitude of this product, ma. So use and that's all I want to say about it. Next question, please. All right. I didn't see who was first. Okay. You just want to prevent me from starting the new topic, I know. All right.
We have these 4 minutes. You couldn't get it. I didn't really understand what happened with when you switched the bicycle wheel yesterday. So you fell. When you switched the bicycle wheel turning versus you turning. You're going to do it.
I know. Well, the initial situation supposed to be looking like this. And let's say this is the bicycle wheel, which spins like this. So what First of all, the axis of rotation in this situation is vertical. When the wheel is spinning like this, it tries to kind of bend the rotating table, but this is our z-axis. And the spinning wheel, of course, has a certain momentum, but it's horizontal. It doesn't affect vertical motion. So initial z equals 0. But when I make it up, let's say it was spinning like this. Now, relative to the axis, the wheel has certain angular momentum. Since total momentum of a system was 0, to compensate that, the turntable with the person or wherever it is also should start spinning, but in opposite direction. So the total angular momentum of the system would remain 0. Initial was 0, and that should be, again, 0. And if you flip the wheel, in that case, the turntable also should start spinning in opposite direction. That's it. If you start from 0 angular momentum, it must remain to be equal to 0. Yep, well, this is, yeah, well, so you have to start from this, and then you put it up and start spinning in opposite direction. And then you turn it down and start spinning again in opposite direction.
Are you spinning in the same direction?
Well, it would, if the same direction, it would, depending on it, it would make you spin faster or slower. This is, I can show you again. The gyroscope. Oh, thank you. Well, please, today I'm taking, again, surprise attendance. Please, before leaving the room, find your name. They're all identical. Don't sign 5 times.
I noticed for one example a few days ago you used the equation for inertia for a ball as a small mass, and today you did it as a sphere.